Okay, so welcome everyone. Thank you for joining this session of the virtual seminars in economic theory. Today, we're very happy to have Emir Kamenica, who is going to present comparisons of signals with Ben Brooks and Alex Frankel. And we're very pleased to have our guest panelists, Philipp Strack and Omer Tamuz. The format of this seminars is as follows. We have a 60-minute presentation with time for interview questions from the panelists and the audience. And you can also post any comments you have in the chat, or you can unmute yourself and ask a question. The talk is recorded. And at the end of the talk, we're going to have a short Q&A session discussion. Before I hand over to Emir, let me invite you to our next seminar, which is going to happen next week. Sulanya Dasgupta from Chicago is going to talk about screening knowledge, and guest panelists are Ian Ball and Rahul Deb. More information on our website and on our Twitter. Thank you. Emir, the screen is yours.
All right, thank you very much. So again, my name is Emir Kamenica, and this is joint with Ben Brooks and Alex Frankel. I'm going to jump in and just start not with some, broad introduction about importance of information in society, and just start with a terminological distinction. And this is not a standard terminological distinction, but it is becoming more common. And in any case, I want you to embrace it for the duration of this talk. One way to formalize a source of data is as a Blackwell experiment. I'm going to be calling it experiment for short going forward. What is a Blackwell experiment? Blackwell experiment specifies the distribution of its data conditional on the underlying truth, i.e. the state of the world. So it's a map from the truth to some distribution over data. So experiment is basically a data generating process. I'm going to use a different word, namely signal, for a formalization of a source of data that provides a bit of a richer description. To describe a signal, you need to tell us what the distribution of the data that signal generates is conditional on the truth, the state of the world, but also on the data generated by any other signal. So our definition of a signal will be such that will encode the correlation between this source of data and other sources of data. It's easy to see that there's, one sort of big benefit of this is that if you know how to combine sources of data when they're construed as signals. Specifically, if I specify multiple experiments, I tell you, Ann has experiment A, Bob has experiment B, good. I know how much Ann knows. I know how much Bob knows. That doesn't tell me what would happen if I got to see both Ann's and Bob's data, unless I make some implicit or explicit assumption that their data is conditionally independent. So if there's potential correlation between sources of data, I don't know how to determine the informational content of multiple sources of data, of information construed as experiments. By contrast, since the signal tells me the correlation with the state, but also the correlation with any other signal, when I specify multiple signals, I've told you both what Ann knows and what Bob knows, but I've also told you how much I would learn if I got to see what both of their sources. In many applications where this is super important, obviously when you think about whether source information are complements or substitutes, you need to be worried about their correlation. Sort of less obviously, there is a distinction that's not that widely sort of discussed within economics, but there's really nice work in formal political science on it, in political economy, on the distinction between voting and deliberation. One way thing about voting is that, each of us can be thought of as just having an experiment. Okay, now those experiments may or may not be correlated, and we're just sort of voting on which way to go. So I say we should all go right. Someone else says we should go right. You don't know from those votes whether our reasons are independent or there's the same reason why we're both voting right? Because we haven't merged our data. Deliberation, by contrast, sort of merges what I know, what you know. So I'm telling you should go right because of X. It's like, well, I was just about to say that. So sort of we know that my vote is repetitive for your vote because it's based on the same reasoning. And in order to think about things like that, we really want to be thinking of each of our information sources as signals rather than experiments. Matthew Jenska and I worked on some questions related to competition persuasion. And in that work, it was really important to think about information being provided as signals rather than experiments. More generally, whenever you worry about higher order beliefs, signals are the object you want to think about. All right, the research agenda that this paper is a part of is comparison of signals. There's a sense in which there was very little choice in what to title this paper, given what it's about. In the 1950s, Blackwell taught us how to compare experiments. In particular, one important question, the answer is, how can I determine whether one source of information construed as an experiment is more valuable than another, regardless of decision makers' preferences? A kind of question that's actually, it's not just that, it's hard to answer, it's hard to even sort of ask when you think of experiments as a source of data as signals, is when is one source of information more valuable than another, regardless of preferences, but also regardless of any other information that the agent might have. So the big picture is going to be that Blackwell was agnostic about preferences, but implicitly dogmatic that the two sources of information are being compared are the only information in the world. We're going to sort of extend our agnosticism and be both agnostic about preferences and agnostic about sort of background information, okay? That's the big picture agenda, but we'll be doing a few other related things as well in comparing signals. To make this a little bit more concrete, suppose I want to ask myself whether a subscription to the New York Times is more valuable than a subscription to the Washington Post. Now, the answer might be that the answer is, it depends. It depends on what I'm interested in. But Blackwell's theorem tells us that sometimes I can conclude that New York Times is more valuable than the Washington Post, regardless of what I'm interested in, right? Blackwell tells us that if, in fact, the distribution of posteriors that I get from reading the New York Times is the mean preserving spread of the distribution of posteriors from the Washington Post, then New York Times is a more valuable subscription, regardless of the underlying preferences. Okay, that's just restatement of Blackwell's theorem. That answer, however, really implicitly relies on there being exactly two potential sources of information. Either I get the New York Times or I get the Washington Post, and that's it. Okay. What if I already have subscription to the Wall Street Journal? We cannot just look at what New York Times does on its own in terms of distribution of posteriors induces and what Washington Post does, because it could be that New York Times plus Wall Street Journal is less valuable than Washington Post plus Wall Street Journal, because, say, New York Times and Wall Street Journal report in the same way, or Washington Post and Wall Street Journal are complementary in some sense. So we want to answer the analog of Blackwell's question when there's a background information such as the Wall Street Journal. Okay, let me give you a very quick overview of the results. The Blackwell order, I'll be using a letter like tau for experiments. Blackwell order tells us when one experiment tau is more valuable than some tau prime for any action set and utility function. The state space is fixed in the background, as is the prior. I'm going to introduce a strong Blackwell order, which will be an order on signals. And I want the source of information model as a signal pi to be more valuable than pi prime for any action set, utility function, and background signal pi hat. Okay, so that's a definition. Another definition is an order on signals called reveal or refine. I'm going to say that pi reveal or refines pi prime if pi reveals the state. So I learned the state when I observe the outcome of pi, or if I don't learn the state, then I learn what I would have observed had I seen pi prime instead. When that's the case, I'm going to say that pi reveal or refines pi prime. And our first theorem says that pi is above pi prime in the strong Blackwell order, if and only if pi reveals or refines pi prime. So we have a very sort of tight, necessary, and sufficient condition for the extension of the Blackwell order to the potential presence of background information. Once we start thinking about combining information sources, there are other economically natural comparisons that arise. Perhaps most obviously, sufficiency. Okay? Sufficiency, as analogous to statistical sufficiency, as you know, has been used in various places in economics. For example, in Holstrom has some results that relate to sufficiency in contracting problems. The definition of sufficiency that we're going to use is that pi is sufficient for pi prime if once I have pi, the marginal value of pi prime is 0 in any decision problem. In other words, pi plus pi prime is never strictly better than pi on its own. Okay, that's going to be the definition of sufficiency. And it's going to turn out that refinement, which I haven't talked about yet, but refinement just tells us pi refines pi prime if pi observes everything pi prime does. Refinement is going to turn out to imply, but be strictly stronger than sufficiency. And sufficiency implies, but is strictly stronger than Blackwell. Another potential way to order signals is what we term the Martingale relation. This one is a little less intuitive, a little bit harder to explain, but it has some interesting properties. I'm going to say that pi Martingale dominates pi prime. If the observer of pi prime, that's our less informative signal, expects the observer of pi, the signal that Martingale dominates, to have the same belief as the observer of pi prime has. Okay, it's going to turn out that Martingale is sort of squeezed between sufficiency and Blackwell. So sufficiency is going to imply strictly Martingale, and Martingale is going to imply Blackwell. Okay. Why am I using these subset signals for implies? Well, because these are going to be relations on signals. Relations are a subset of the Cartesian product of signals with themselves. Hence, relations are sets. When one relation is a subset of the other, it means that implies it is a stronger, more demanding relation. Then I want to turn to talking about more general notion of strengthening relations. I talked to you about strong Blackwell, but you can really strengthen anything by requiring that the comparison be robust to background information. So it's a natural question to ask, well, what is strong sufficiency like? What is strong Martingale like? And perhaps surprisingly, it turns out that strong Blackwell, strong sufficiency, and strong Martingale are all exactly the same order. They all are equal to reveal or refine. So while we to sort of zoom out, once we're talking about signals rather than experiments, there's more than one natural way to compare source of information. Blackwell is the natural order in experiment space. In signal space, when we worry about correlations, there's refinement, there's sufficiency, there's Martingale, there's Blackwell, and they're all distinct. But sufficiency, Martingale, Blackwell all become the same relation once we insist they be robust to other information. All right, that's what I plan to tell you. Now let me say all of that a bit more formally. We have a finite state space with a typical state denoted by little omega, interior prior mu sub naught. I'm going to simplify my notational life. There's no substance to this. I'm going to define an experiment as just a distribution over posteriors that, of course, is on average equal to the prior. The more traditional definition of Blackwell uses a map from the state to the distribution over outcomes, but it'll be just easier for our purposes to immediately move to the space of distribution of posteriors and just identify an experiment with the distribution of posteriors it induces, okay? Once I do that, I have an actual partial order on experiments. There would only be a pre-order in the Blackwell definition, a partial order, which is the mean preserving spread, and I have that tau is a mean preserving spread of tau prime denoted with this symbol. A signal is defined differently. And if you haven't seen his definition before, it takes a little bit of effort to digest, but I'll try to do that for you. If you have seen it before, this will be repetitive. Yes. A signal is defined as a partition of the state space crossed with a unit interval. This is a formalism that is closely related, that was introduced basically by Green and Stokey in the 70s, and has sort of been used, has sort of had a little renaissance in the last several years. What is the interpretation? Interpretation is that the unit interval encodes the source of randomness in the data conditional on the state. So the state is realized, and then there's some noisy information. What information will be generated given the state, that is governed by a uniform random variable on this unit interval. Okay. So a signal realization, little s, will just be a subset of the state space crossed with a unit interval. And a signal realization is going to happen in state omega. Probability of S in state omega is just going to be the Lebesgue measure, lambda for Lebesgue measure, of that signal in that state. It's a little hard to digest. It will be easier with some pictures, which I'm going to go to next. I'm going to denote the set of all signals with capital Pi. So here is a way to visualize signals. This is a situation where we have two states, left and right. And this particular signal has two signal realizations, A and B. The probability of A in state L is just the Lebesgue measure, the length of A in the left unit interval, right? The state space crossed with the unit interval is the two copies of the unit interval, the one for state left and one for state right. So the probability of A in state L is, let's say, 0.7 here. And probability of A in state R is like 0.3. So when I see A, my posterior is going to move toward left. B, on the other hand, has a smaller likelihood in state L than in state R. It happens with probably 30% in state L with 70% in state R. So when I see B, my posterior, let's say, was equiprobable, I'm going to move to thinking there's a 70% chance that the state is B. So,
Emir, can I ask a question?
Yeah, absolutely.
So, does the partition have to be finite? I guess I have two questions. Does the partition have to be finite?
Partition has to be finite. Yes, partition has to be finite in order for, so I never said it, but I should have said it. A signal pi is a finite partition of omega cross 0, 1. And the reason we'll really want that is we want to make sure that we're sort of, there's only finitely many zero measure events. And therefore, when we take joins of signals, everything behaves as we'd like. So absolutely, a signal is a finite partition.
And in the usual way of thinking about signals, that means that there's only finitely many signal realizations. That
is correct. There's only finite, any given source of data generates only finitely many signal realizations.
So, I mean, seems, but correct me if I'm wrong, this seems equivalent to just thinking about, take just a standard probability space, the interval 0, 1 or whatever you want, and have the state be some random variable there, some, say, finite partition, then have the signal correspond to some other partition, or more generally, sub-sigma algebra, if you want to allow, or a random variable, right? Have the state be one random variable, have the signal be another random variable.
Okay, yes.
Okay, that was my question. So it's basically...
Yeah, so absolutely. So there's the state, which is the random variable that is the payoff relevant one. And then there's the randomness that governs the signal realization, that's the unit interval. And I'm just focusing on finite things. You'll see the benefits of doing partitions rather than sigma algebras, but those are really notational rather than sort of conceptual issues that I'm going to make everything finite.
Thank you.
Thanks. That was a helpful clarification. Now, if I had only one signal, one source of information, they would sort of be overkill. Why am I drawing these things and saying that, A is on the left instead of on the right part of L? All I really need to know to interpret these data, if this is the only source of data in the world, is the likelihood of A in L and the likelihood of in A versus R and likelihood of B in A versus R. The reason why this is helpful is because, I'll get that in a moment. Let me first, sorry, I'm getting ahead of myself. Note that each signal, pi, induces some experiment, which I'm going to note by brackets pi. And if two signals induce the same experiment, I'm going to call them equivalent and use the similarity notation. we're going to say that a signal pi refines pi prime using the calligraphic R if every element of pi is a subset of some element of pi prime, standard definition of a refinement of a partition. And notice that pi, the set of all signals coupled with the refinement order, is a lattice. Okay? The join of two partitions is a partition, okay? And in particular, it has a clear economic interpretation. Pi join pi prime is a signal equivalent to observing both pi and pi prime. Let me illustrate that and also talk about the benefit of this way of visualizing signals. Here's just pi and pi prime. If I were to look, if only pi or pi prime existed in the world, there would be not a lot of benefit in sort of worrying about the way I encoded them as signal. But once I know that both could exist and maybe they can be obtained together, what this formalism does is it points out that, pi and pi prime, if you look carefully at this picture, you'll notice induce the same experiment. They're equivalent in the definition I just gave. Each of them, if we start with a 50-50 prior, induces a distribution of posteriors 0.3, 0.7. But despite the fact that they induce the same experiment, they're not the same source of information. They're not redundant with one another. Okay, I could have made pi prime equal to pi, but if I did that, this C couldn't be here on the right side of the unit interval. It would have to be right underneath A. Okay. Here, in fact, pi prime sometimes leads to a different belief than the belief that pi would lead to. And therefore, I can talk about what would happen if I observed both of the sources of information. And the answer to that is just by taking their join. And the join, of course, is very easy to see when we stack signals like this. I might see AD, AC, BC, or BD. And it's easy to read off the distribution of posteriors induced by the join of the signals. If I see AD, I'm stuck at the prior because that has the same likelihood in two states. If I see BC, I'm stuck at the prior. But if I see AC, I know for sure that the state is left. And if I see BD, I know for sure that the state is right. So this formalism, coupled with this sort of visual system, this notational system of stacking experiment, makes it really easy to determine the joint informational content of two information sources. Good. Now, let me use this formalism. All of this is sort of background that has been present. Philipp, did you have a question?
Yeah, I just wanted this formalism. In some sense, it's without loss, right? I could always.
It is absolutely without. It's without loss, and we've now actually taken the trouble to pin down exactly the sense in which it's without loss. So let me tell you two senses which is without loss. First, let me note that it's without loss if we're going to do partitions if we are in finite situation. So let's define a type space as being a collection of finite sets and some joint distribution between the state and those finite sets, call them T1 through Tn. It is very easy to show that a signal allocation specifying signals pi1 through pi n is equivalent, formally defined, to any type space thus defined. Okay, there's going to be a bijection between each type and each element of each partition. So that's sort of the easy part. The part that's more interesting, if you think about our interpretation, is if you think about this unit interval, there's two ways to think about the unit interval. One is as some true state, sort of Aumann style, that governs the distribution of data conditional on the state. Well, then that's not a given. And for me to describe what New York Times is, I need to tell you exactly the partition of that true state space. Then there's nothing really to worry about. Another view, another interpretation is that unit interval is not the true state space. It's a modeling device for encoding correlations. And in that case, you might worry that, for example, you say, okay, tell me what New York Times is, and I sort of embed it as a signal. But I sort of made an arbitrary choice as to whether when it says left, that's on the left side or the right side of the unit interval. I sort of chose that arbitrarily. Then you give me the Wall Street Journal. Well, now, I embed that, but I'm careful to get the correlations right. What you might ask yourself is, might you ever regret the choices that you made once you find out what else you need to correlate with? Because there's many ways to encode New York Times under this modeling device interpretation as a signal. And we have a result. It doesn't require a lot of work to show that, in fact, you would never regret it. You could sort of embed any information source into the state space cross-video unit interval myopically, not yet knowing what other information sources will show up and how you will need to embed them to make them suitably correlated. Does that answer your question?
Yes, thank you.
Omer?
Emir, sir, just about this works for finite partitions, right?
Finite. If you want to do infinite, then instead of signals, we're going to have sigma algebras. We're not going to have joins. We're going to have more complicated things. Everything I just said is finite.
Okay.
Absolutely. Good. Let me turn to the strong Blackwell order. First, let's remind ourselves what Blackwell is about. A decision problem is a pair that consists of a compact action set, A, and a continuous utility function, little u. I'm going to use script D to denote the class of all decision problems. What's the value of a particular source of information construed as an experiment, tau, in some problem D? Well, that's easy. An experiment tau gives me some distribution of posteriors. Here it is. For every mu tilde in tau, I'm going to maximize, by choosing the appropriate action, my expected utility with the belief mu tilde that was drawn from tau. That's the value of the experiment. Okay, this is mainly expected payout. This is not relative to no information. You could, of course, subtract minus what you get with no information, but since we're comparing experiments, that's not particularly helpful. And Blackwell tells us that tau is more valuable than tau prime for every decision problem, if and only if tau is a mean preserving spread of tau prime. Okay? There's nothing new here. This is 70 years ago. Now, of course, we can restate this in signal space very easily. The value of an experiment tau in problem D, I'm just repeating what I had on the last slide. If you want to think about the value of a signal in problem D, all you do is you just replace the signal with the distribution of posteriors it induces, and the value of the signal is the value of the induced experiment. So that really, if this was all that was happening, we're just doing Blackwell, there would be no point in going to signals. But we want to, so by the way, note, as an aside, we're going to say that pi Blackwell dominates pi prime if signal pi has higher value for all decision problems. And notice this might seem sort of picky, but actually it foreshadows things that might become interesting. This is a relation, not a partial order, okay? Because it's not anti-symmetric. And as we'll see, some interesting comparison of signals will not even be transitive. So we want to, this is why we're going to be talking about relations on signals rather than general orders, pre-order, partial orders, because that would be too restrictive. An extended decision problem, the hat, consists of an action set, a utility function, and some signal pi hat. But the interpretation of pi hat here is the exogenous information already available to the decision maker. Okay. Script D hat is the class of all extended decision problems, and the value of a signal in some extended decision problem is really easy to denote because of the lattice structure on signals. How valuable is pi in problem D hat? All I do is I take the join of pi and pi hat. Pi hat was already there. Now I have pi as well. I get pi join pi hat. That induces some experiment. And I look at my expected payoff. And then we're going to say, Omer.
Sorry to interrupt, but before I didn't quite understand why the Blackwell order is not a partial order, isn't it? Because the Blackwell order,
Blackwell relation, just because two in the space of signals, two signals can be distinct, but each one Blackwell dominates the other because they induce the same distribution of because they induce the same experiment. That's all.
Okay, thank you.
It's definitely transitive. Strong Blackwell order, strong Blackwell relation will be transitive. It's just not anti-symmetric. Good. So here's the key definition. Pi strongly Blackwell dominates pi prime, denoted pi, the upper bar pi prime. This upper bar will come back later and for more general uses. If pi has a higher value than pi prime in every extended decision problem. Good. So that's what we're sort of now after. We want to characterize strong Blackwell dominance, similarly like Blackwell characterized Blackwell dominance. And before telling you how to characterize it, I want to discuss that there might have been two other natural ways to think about robustness to some other information. First, we could have taken an ex post perspective. Instead of thinking about an agent when comparing New York Times and Washington Post that has a subscription to the Wall Street Journal, we could have talked about an agent that has heard a piece of news. So I'm not talking about an agent having another information source. I'm talking about an agent having a pre-existing piece of information. What's a piece of information? It's just a signalization S. Okay. So we could have demanded, instead of demanding that pi is better than pi prime for any AU pi hat, we could have demanded pi is more valuable than pi prime for any AU little s. That would have been for the ex post instead of the ex ante perspective. Another thing we could have done is we could have made that other information not exogenous, but endogenous. So imagine that I could give you pi or I'll give you pi prime. You don't have any information to start with. Once I give you pi or pi prime, you may now choose, because you're unhappy with the amount of information I gave you, to go and gather more information at some cost. So we could add to the actions of the utility function not some pre-existing information, pi hat or s, but instead add some cost function c that specify how costly will it be to acquire additional information once I give you pi or pi hat. And we could have demanded pi is more valuable than pi prime for any such problem. So you might worry we now have sort of an embarrassment of riches, and we're going to have a laundry list. And for each of these notions, we're going to have to characterize when is one more valuable than the other. If we have the ex ante perspective, the ex post perspective, the endogenous acquisition perspective. But it turns out that's not an issue because the three definitions are equivalent. So everything I say about properties of strong Blackwell applies equally well to any of these three notions of being robust to other information, whether it's ex ante, ex post, or endogenously acquired. Good? Now that I'm sort of telling you why you don't need to worry about our particular choice of how we define strong Blackwell, let me characterize strong Blackwell. To that end, I say that pi reveals or refines pi prime if every possible piece of data generated by pi, those are the sets little s in pi. Like that's the data that can come out of pi. Pi is just a collection of these s's. When I see a piece of data from pi, either I'm going to learn the state for sure. How does that happen? That happens if the probability of the state is strictly positive for at most one state. So it cannot happen with multiple probability in multiple states. Or if this isn't the case, if it's not true that pi has taught me the state, this signalization of pi must be a subset of some s prime and pi prime. The interpretation is I learn what I would have seen had I gotten pi prime instead. So reveal or refine basically says I either learned a state, so my first order belief is degenerate, or I learned what the other person saw, in which case my second order belief is degenerate. Either my first or second order belief has to be degenerate when I see pi, if pi reveals or refines pi prime. Or second order belief, of course, refers to the beliefs of an agent that sees pi prime. It's easy to check in our way of depicting signals whether, in fact, reveal or refine relation is satisfied. So consider these two signals, pi and pi prime. I want to try and convince you that pi reveal or refines pi prime. What do I have to do? All I got to do is there are 1, 2, 3, 4 signal realizations in pi, and I'm going to go through each of them. There's just 4 of them, and check for each of the 4 of them. Do they either teach me the state or teach me what I would have seen under pi prime? And that's easy to see. Let's start with K. K is an overachiever. It both tells me that the state is L and tells me I would have seen G had I gotten pi prime instead. So it both reveals and refines, therefore reveals or refines pi. N does not tell me what I would have seen had I seen pi prime, but it does tell me that the state is L and only happens in state L, so it passes the test. O does not tell me the state, because O happens both in state left and state right, but if I see O, I know I would have seen H had I gotten pi prime instead, so it passes the test. And finally, P tells me the state R, and it passes the test. Therefore, I conclude that pi reveals or refines pi prime. So I've shown you that it's sort of easy to check. Why might you want to check it? Well, because of our first theorem, pi strongly Blackwell dominates pi prime, if and only if pi reveals or refines pi prime. The proof is pretty straightforward. The if direction is almost trivial. First, we observe that if pi is more valuable than pi prime for every possible realization, then it must be more valuable overall, okay, just by integration. And if S reveals the state, obviously pi is more valuable because nothing can be better than learning the state. We have a decision problem, right? We don't have a game. And if S tells me what S prime would have been, if S is a subset of S prime, then whatever other information I see, some S hat, it's got to be that S intersection S hat tells me what I would have seen under S prime intersection S hat, and therefore pi plus whatever generated S hat has to be more valuable than pi prime plus whatever generated S hat. Okay, that's the if direction. Given the time, I'm not going to go through the only if direction. Let me just note that it's constructive. So you give me pi and pi prime, which are not ordered by reveal or refine, then the proof tells you how to construct a pi hat so that the lower signal becomes more valuable once pi hat is added. Okay, and here's the specific construction, which is a little too elaborate to get into, given I have 22 minutes left.
I know that you only have 22 minutes left, but I have a question.
That's fine.
So I have this intuition that I can't exactly square with this. So I was wondering, imagine that my state is two-dimensional. So, you know, there are four possible states, and omega 1 is low or high, and omega 2 is low or high. And I have two signals, and one of them, what it does is so pi refines pi prime with respect to one dimension, and it reveals with respect to the other dimension. But nowhere does it completely reveal or completely refine. But it's still, you see what?
We remember we have to have pi plus anything more valuable for any decision problem. Now take the dimension where pi does not reveal the state. Take the dimension where pi is not revealing the state. Then now I'm going to build a signal so that pi hat, such that pi prime plus pi hat, they're going to be complements. They will fully reveal that state.
But it refines in the dimension where it doesn't reveal, it refines the other signal.
Okay. But I think the problem is it might not be complementary to the new signal you add. It refines it, but it might be redundant with the additional signal you might add in addition.
Exactly. It doesn't refine it overall. It's the complementarity is going to come along the dimension where it doesn't refine. And it's going to end up revealing the state that's payoff relevant.
Okay, thank you.
Thanks, Philip. Good. All right, so if I ended here, this would be a coherent exercise, right? That you could imagine a paper that just stops here. But it turns out that, the origin of this paper is us actually realizing there's a lot of interesting ways to compare information sources once we are in the world of signals rather than the world of experiments. Okay? And one such way to compare things is sufficiency. So I'm going to say that pi is sufficient for pi prime, written pi as pi prime. If the value of pi, and of course we've defined the value of a signaling, is the same as the value of pi join pi prime in any regular decision problem, not extended. Okay, so in other words, once I see pi and you want to try to sell me pi prime, I have no value for buying pi prime, regardless of what A you were in. And obviously, this looks a lot like the notion of statistical sufficiency in statistics. Okay. It has a clear economic interpretation. I'm not asking, is New York Times more valuable than Washington Post? That's Blackwell. I'm asking, once I already have a subscription to New York Times, is there any value to subscribing to Washington Post in addition? If the answer is no, then New York Times is sufficient for Washington Post. There are equivalent definitions. The equivalence is relatively straightforward. We want the experiment induced by pi join pi prime to be the same as the experiment induced by pi. That's equivalent. Given any omega x, observing pi must induce the same beliefs as observing both pi and pi prime. Okay, what this basically tells you is that not only are the experiments the same, which doesn't mean distributions are the same, but the random variables of beliefs of pi join pi prime and pi are the same random variables. Okay, they're perfectly correlated. And perhaps the most commonly seen definition of sufficiency in statistics textbook is for any state, for any S, that's our higher signal, and any S prime, that's an element of the lower signal, probability of S prime given S and omega is independent of omega. In other words, once I've seen S, S prime cannot teach me anything about omega because conditional on S, S prime is independent of the true state. Okay. It's going to turn out that this middle definition will be the one that's most useful for checking sufficiency in our visual notational system. So I want to try and convince you that pi is sufficient for pi prime. To do that, I make my life slightly easier by pushing them one row down, keeping a top row open, and putting the join above pi instead of down here, because I really want to be comparing the top signal pi with pi join pi prime. And what I want to tell you is that what I need to convince you of is that had I gotten both signals, I would end up in any possible circumstance, any omega x, I end up with the same belief as if I'd just seen pi. Okay, that's easy to see. If I see G and K from the two signals, well, I would have seen K and pi, and that would have led to the same belief, to the same signalization. If I see G and L, well, because G and L have the same likelihood in the two states, I know that leads to a posterior equal to the prior. But had I not seen pi prime, I would have just ended up with L. But L also has the same likelihood in the two states, so it would have led to the same belief, etc. So this is the way you check for sufficiency. A few remarks about sufficiency. Refinement implies sufficiency, which in turn implies Blackwell. I'm not going to go through the proof of that, but it is the first part's immediate. The second part requires a little bit of thought. And the other thing that's worth noting is that sufficiency is not transitive. This is sort of what I was hinting at, what I was foreshadowing, properties of these comparisons, that they're not all going to be partial orders. The fact that sufficiency is not transitive is easily seen with an example. This example is actually quite instructive independently of its use in this proof. Consider these three signals, pi A, pi B, and pi C. On their own, they're all worthless. Neither of them by itself teaches me anything about the state. Pi A has signalizations V and W, each of which happens with a 50% chance in state L and with 50% chance in state R. Pi B is like the least informative signal imaginable. All it ever does is just say U. Okay? It doesn't teach you about the state, and it doesn't teach you about the payoff element state, nor about what any other piece of information would tell you. And pi C looks a lot like pi A, but it's different. It has two signalizations, S and T, and each happens with probably a half in each state. So each of these three signals is entirely uninformative on their own. I'm going to argue that pi A is sufficient for pi B is sufficient for pi C, but pi A is not sufficient for pi C, thus violating transitivity. It's easy to see why this is the case. As I just mentioned, each of the signals on their own induces the uninformative experiment, completely uninformative experiment tau lower bar. Moreover, adding B to A just gives me A back, and that's uninformative. Adding C to B just leads me to C, and that's an informative. So there's no added value when you add B to A or add C to B. However, if I add C to A, and now I get VS as a potential outcome, well, VS tells me the state must be left. WT tells me the state must be left. WS tells me the state must be right, and VT tells me the state must be right. So in fact, A and C are highly complementary. Together, they perfectly reveal the state. And therefore, we don't have transitivity. And, this should look familiar from sort of computer science methods on creating distributed keys. Another way to compare information sources, which we understand less well, for me to be perfectly honest, we're going to say that pi martingale dominates pi prime, denoted with calligraphic M, if the expected belief, that's the mu tilde, of a person who observes pi, given the data for pi prime, is the belief of a person who observes pi prime. And there is this very important caveat, which I'll come back to in a moment. This needs to hold for any prior. So far, I've just fixed the prior in the background. Now, his definition might look a little funny because I'm saying this holds for any prior. What does this mean sort of outside of the mathematical equation? Suppose I read the Washington Post. Do I think that the reader of New York Times holds my belief in expectation? So not necessarily my belief, but the average belief, on average, the belief of the New York Times reader will be the same as mine. The answer, of course, is going to be no if Washington Post is extremely informative and New York Times is not. Because suppose Washington Post teaches me the state. Well, then my belief will either be 0 or 1. And the distribution of beliefs, if someone reads the New York Times, will be somewhere in the interior because New York Times does not teach you the state. So in this case, we would not be the case that the New York Times martingale dominates Washington Post. In fact, when something is perfectly informative, it's not going to be martingale dominated by something that's noisy. This is the loose sense, kind of the best I can do in telling you why martingale domination has something to do with information sources, with how informative sources are.
Emir?
One thing not to get confused about, just one thing, Omer, let me finish one thing and I'll take your question. One thing to not get confused about is martingale property is well understood. And martingale property comes from the fact that refinement implies martingale. If you just add information, then the additional information, that's going to be something that's refinement. Pi join pi prime, of course, refines pi. And it's always going to martingale dominate it. So refinement, in fact, implies martingale. That's the well-known result about martingales. When we say beliefs are martingale, that means refinement implies martingale. But it turns out there's more to be said that refinement implies martingale. That is the known result. What we think is more interesting thing that's being uncovered is, as I already told you, refinement implies sufficiency, which implies Blackwell. Well, it turns out refinement implies sufficiency, which implies martingale, which implies Blackwell. Omer, go ahead.
So when you have refinement, then one signal is a garbling of another with a deterministic map that just calculates, the realization of one given the realization of the other. This seems like it's related to a random map that somehow calculates one signal given the other, with maybe an additional source of randomness that you need to add to your space or something.
In a sense, that's right. If all states were payoff relevant, if we were in sort of Aumann style modeling, where we just said, look, there's no such thing as a payoff irrelevant state, then these notions would all collapse on one another. Like, this is an interesting project only in the world where we think that there's some payoff irrelevant set of states that don't enter anybody's utility function. They only serve to generate noise in the data conditional on the state. And everything you said is right by determinism. In fact, if our decision problems, remember our utility function in the definition of a decision problem, importantly, the utility function depends on the action and the omega. The unit interval is being excluded from the set of things that a utility can depend on. If we redefine this continual function to be u from a cross omega cross the unit interval, and then we wanted to be valuable for all decision problems, then none of this would be of any interest, and we'd in fact have all of these four comparisons to be one and the same. Refinement equals sufficiency equals Martingale equals Blackwell. I'm not sure if that gets a bit of what you were saying.
No, I think I was thinking something a little different. But I think that there might be a way to get a description, an equivalent description to this Martingale property in terms of one signal being a refinement of the other signal in a slightly larger space where you've added more randomness. I don't know if that makes sense, but maybe we
but I feel like the state space I wrote down is all of it. There's no like anything.
You can always throw in more randomness. Just add in another 0, 1.
But I know this Martingale condition is relying all these beliefs that whose expectation we're taking, all of the randomness is just coming from the unit interval. And I think I may not understanding what you're saying. Philipp was going to maybe comment whether to.
Yeah, maybe you can keep it inside the unit interval, but basically let's maybe take it offline now.
Okay. I do want to tell you about one more theorem. So let me just quickly note that Martingale is not transitive, just like sufficiency. And you can come up with examples where this condition holds for some priors and not for others. There is, in the appendix of our paper, there's a part of the appendix that you should not read that does really cumbersome characterization of the various versions of Martingale. This one I'm talking about sort of the for all priors. You can also talk about Martingale being, or there exists a prior, and those are ordered, and they're both between sufficiency and Blackwell. And I think that's more than we want to know about the relationship between Martingale and prior variance. Let me take the little bit of time I have left to tell you about strengthening in general. The notion of strong black will try to make the Blackwell comparison robust to other information. And obviously, you could apply the same idea to sufficiency. And you could apply the same idea to Martingale. More generally, you could play, so what would it mean to apply to sufficiency? Would say that pi prime adds no value to pi in any decision problem, but not any regular decision problem, but any extended decision problem. Okay, so I have someone that has a u pi hat, they already have pi hat. Is it a case that pi prime doesn't add any value? Notice that the presence of pi hat could change the marginal value of pi prime because perhaps pi prime is complementary to pi hat. And we're allowing for any pi hat. In general, given any relation P on the set of signals, we define strong P, denoted P upper bar, as follows. Pi is strong P above pi prime if pi joined pi hat is P above pi prime joined pi hat for any pi hat. Okay, so pi is strong P above pi prime if pi plus anything is P above pi prime plus that same thing. Good, and obviously strong Blackwell was a specific case of this. This would be another definition of strong Blackwell is pi joined pi hat. Blackwell dominates pi prime joined pi hat for any pi hat. So now natural questions is, what can I tell you about strong sufficiency? What can I tell you about strong Martingale? Before I do that, I'm going to first note some general properties of strengthenings that do not depend on P. In general, strong P is a stronger relation than P. Strong P implies P that's immediate because pi hat could be the null signal. For example, that signal that always said U. So obviously, if you're strongly above, you're above. Importantly, strengthening is monotone. If P implies P prime, then strong P implies strong P prime. And lastly, in terms of general properties, it's idempotent. Okay, strong P is just strong P. This is immediate to see because, pi hat 1 join pi hat 2 is just some pi hat. So, this none of these require any proof. One thing I'll note is, strengthening is weakly stronger. Some relations like refinement are unaffected by strengthening. Okay, if pi refines pi prime, then pi strongly refines pi prime, because obviously if pi refines pi prime, pi join pi hat refines pi prime join pi hat. Good. It's going to turn out that these two properties of monotonicity and idempotency are going to be incredibly useful for telling us about what strong sufficiency and strong martingale look like. Here's the general version of the result. We actually have a stronger version of this, but given the time, I won't get into it. But there's a way to actually generalize this result even further. Let me tell you the result I actually have on these slides. Suppose P is a relation on signals, and it's a relation that's weaker than strong Blackwell, but stronger than Blackwell. So, for example, P could be sufficiency or P could be martingale. We know sufficiency and martingale are in between. Well, then it's going to turn out that pi strong P above pi prime, if and only if pi reveals or refines pi prime. Corollary of this, of course, is that strong Blackwell equals strong sufficiency equals strong martingale. The proof is 2 lines. Okay, let's take some relation that's weaker than strong Blackwell but stronger than Blackwell. Starting from the fact that it's weaker than strong Blackwell, applying monotonicity tells us that strong Blackwell implies strong P, but then idempotency tells us that strong Blackwell implies strong P. Starting with the second part of what we assumed, namely P implies Blackwell, just implying monotonicity, just using monotonicity tells us that strong P implies strong Blackwell. We've talked a lot about complementarity. These two conclusions are complementary. You put them together and you get that strong P equals strong Blackwell, which of course equals reveal or refine. Good. I'm right on time. I want to end by putting up a picture that encapsulates this string of comparisons relations. Okay. Strong refinement is equal to refinement. Refinement is strictly stronger than strong sufficiency, strong martingale, and strong Blackwell. Strong Blackwell is strictly stronger than sufficiency. Sufficiency is strictly stronger than martingale. Martingale is strictly stronger than Blackwell. So the title of Blackwell's paper is Equivalent Comparisons of Experiments. What I've just presented to you is several non-equivalent comparisons of signals. But what's really interesting is, despite the fact that they're not equivalent, several of economically interesting relations of signals do coincide once we consider their strengthened versions. And I promised you pictures, a picture that sort of illustrates all of the negation signs that you see here. So pi naught here is just there to be beaten up on. And then Blackwell, pi b, Blackwell dominates pi naught, but pi b is not, I'm sorry, and pi m should be in here. This is just an older picture, so I apologize. Pi m should be right here between pi s and pi b. You could definitely put pi m in here and still check everything. So sorry about that. But pi b, Blackwell dominates pi naught, but it doesn't martingale or sufficiency or strong Blackwell dominate. Similarly, pi s is sufficient for pi naught, but it isn't strongly sufficient, doesn't refine, etc. And I'm out of time. One last thing to say. We think of this paper being is a paper, but we hope it's also just part of a relatively undeveloped at this time agenda on comparing information sources once we are concerned about correlations. We have results in the paper that are not in the talk today, but they're also open questions that we haven't solved yet. Understanding better issues of non-transitivity, understanding when relation of signal is such that if pi is above pi prime, then anything that refines pi is above pi prime. That's not going to be true for all the relations I showed you. We can think about what are some ways to sort of provide micro foundations for some of these relations. We don't really have a good one for Martingale. We've been spending a fair bit of time recently thinking about natural cost functions to put on information sources construed as signals. There's been great work recently, including by people on this Zoom call on how to axiomatically microfound good cost functions for experiments. To our knowledge, no one's really thought about this yet for signals, and we've made some progress, but not much. So I think it's an exciting playground to do things in, and being able to draw these pictures kind of makes it a bit easier to work it than otherwise would. All right, maybe I'll stop sharing at this point.
Great. Thanks a lot, Emir. Great talk. We will proceed now with some comments from our panelists. So first, Philipp, if you have any comments.
I don't have any comments. I'm very curious about what is the kind of gap between Martingale for all priors and Blackwell? Like, what is there an easy way of understanding where this gap is coming from?
I think the honest answer.
Oh, sorry.
I think my honest answer is no. In general, I have to admit that I understand the Martingale relation least well of all of these, and have a hard time. All of the sort of ways of checking it seem a little sort of computational instead of, intuitive. So I think it's a good question. It's a question that deserves a better answer, but I do not have a better answer.
Thank you.
So,
Omer?
I want to say this is related to what Philipp asked, and I think that's very interesting about this. What exactly this Martingale means, because it's related to what I said before. So, when you look at refinement, if you think of these signals as just random variables, right? I observe something, this random signal realization. Refinement means that there's some function f, so that one signal is f of the other signal, right? I just calculate one signal using the other. Well, I'm not 100% sure, but what I think Martingale should mean is the following. So when you have this interval 0, 1, the nice thing about the interval 0, 1 is that there's a lot of randomness in there. Even after I chose some partition, there's always enough randomness in there to choose another one. And maybe that's...
Let me just say something I do know. What we really need for all of this structure, the assumption we need is that this auxiliary state space, which we've made the unit interval that's uniform, all I need is that there is some auxiliary space X, and a atomless distribution on it. And in particular, the property of non-atomicity that we need is take any event and any number between 0 and 1, there is a sub-event that has exactly that share of probability. So for any event E, number P, there's a sub-event E prime with probability lambda times the probability of E. That's the property you need. That's basically, once you have that, everything goes through. Unit interval with a uniform distribution has obvious sort of expositional benefits.
Yeah. So good. So when you do refinement, you have that S2 is f of S1. I think what the Martingale should correspond to is the following. Take S1 and S2. Because you have this atomless property and you have so much randomness left, you can find a new thing, let's call it R, which is something that's independent of the state and S1 and S2, right? I can find a random variable taking any number of realizations that I want that is independent of everything. And then S2 should be a function of S1 and this R.
Yes,
I see some people saying no, but I suspect it may be something like this. Bo, and I see you disagree, or oh no, okay. Maybe my intuition is wrong, but
no, I mean,
something like that.
I'll be honest. This is the kind of thing I'd have to write down. It's a little hard to
I understand.
Picture without pen and paper, but it doesn't sound wrong to me. It sounds right. So
it's basically it's a garbling, but implemented within your probability space. It means that S2 is a garbling of S1, but this randomness from the garbling also comes from within the space.
Yeah, but I do think this is complementary to Philipp's question, because of course this does require, Martingale, there's a gap between Martingale and Blackwell, right? So we know that.
Oh, sorry, yeah.
So we know that it can't just be that it's, we have to be careful exactly what we mean by garbling, but it can't just be garbling as construed in Blackwell.
Well, yeah, it's like two random variables. You can have stochastic dominance between them, but it doesn't mean that almost surely one is above the other. They really have to be embedded together in the right way in the probability space.
And this is all about, which by the way is worth, one thing that often can be confusing is one way that Blackwell's theorem is often summarized is that, Blackwell dominance equals sufficiency, and that you might say, how, isn't that true? How did you have this gap between sufficiency and Blackwell? Really, it's sort of a pretty strangely quantified result if you want to do the Blackwell result. It's sort of, Blackwell is agnostic about the underlying probability space that governs the randomness. So really, that version of Blackwell theorem says Blackwell dominance is equivalent to an existence of an underlying probability space such that we have sufficiency. Whereas we're not allowing ourselves to sort of choose the underlying probability space sort of after the fact. It's there. It governs the correlation between information sources, and hence you don't have to be sufficient in order to be Blackwell more informative.
Okay, so do we have any other questions from other people? You can unmute and ask. Zisang.
Sorry, I was a bit late. So I'm going to ask about the interpretation for your extended decision problem. Like you're thinking there's another information source that's possibly available. And then for that comparison, you're also interpreting as if the decision maker knows exactly how the information structure or the signal is in hand is correlated with the supposedly pre-existing signal. Is there
let me respond to that. I am not assuming that the decision maker knows is without loss of generality to use a notational system such that within that notational system, they do know. This goes back to sort of, think about Aumann's agreeing to disagree theorem. Nowhere in the statement of agreeing to disagree theorem does he say, agent 1 knows the partition of agent 2 and agent 2 knows the partition of agent 1. He doesn't make that assumption. That assumption is embedded in the definition of what a state is. If agent 1 in Aumann's world did not know the partition of agent 2, that's another dimension of the state space. Add that as a dimension of the state space, redraw the partitions. Now, by fiat, agent 1 knows the partition of agent 2 and agent 2 knows the partition of agent 1. Similar thing can be said here. If you tell me that an agent doesn't know what's the correlation between the New York Times and the Washington Post, good. There's a state of the world which governs that correlation. Add that to the state space, and now it's without loss to say that what the agent knows.
Okay.
Does that make sense?
Yeah. And also related to this question, I think we have this result going from Blackwell to Lehman where we restrict the decision problems. Do you think you have something to say where you can?
I actually do. It wasn't a talk when I said I could extend. It turns out that it's easy to see that strong Lehman equals strong Blackwell equals strong sufficiency equals strong Martingale. I did not tell you that, but it is true.
Okay.
Why is it true? It's true because suppose our construction of strong Blackwell is suppose one thing does not reveal or refine the other, then I can find a state or a pair of states such that they're not distinguished by the top signal. So pi does not distinguish two states, but I can find some pi hats so that pi prime and pi hat together distinguish those two states. That means that take any way of comparing information sources, including Lehman, that makes being able to distinguish some two states valuable, the strong version of that will be equal to strong Blackwell. And we're currently revising a paper to make this into a formal proposition, but basically any way of comparing information sources says there's a decision problem such that you care about distinguishing two states. If you strengthen that, you end up at reveal or refine. So Lehman is definitely covered.
I see. Thank you.
I wanted to ask one question as well. So in terms of the reveal or refine condition, I mean, let me give you another condition if you can sort of think what's the relation. Suppose that I say that pi sort of is better than pi prime if for every x, so for every sort of signal, irrelevant signal, the partition that is induced on the omega is finer from pi to pi prime. So is that
well, the partition is not conditional on a particularization of x. I mean, there's the partition, one partition being finer than another, that is refinement. And refinement is definitely more demanding than, I mean, a simple way to see that refinement is not going to be equivalent in any way to strong Blackwell is, think about a really coarse signal that just tells me the state is left or the state is right. That's not going to refine many things, but it's going to be strong Blackwell above anything because it just tells me the state. So usually we're never going to need refinement per se to be equivalent to strong Blackwell or therefore to reveal or refine. Does that make sense?
Yeah. Okay. Okay. Any other questions? Okay, so maybe we can stop the recording, the broadcasting. So thank you very much, Emir, for the talk, and hopefully we'll see most of you next week.
Thanks.